When you say curse.
All right. Can y'all see my screen?
Yes.
All right, cool. We're gonna go ahead and jump right back into this worksheet and do some more of these reactions on here. We've actually gone through all of the reactions here and in these different quadrants. We talked about reactions of alcohols, how to turn alcohols into carbonyls, what some of the reactions that carbonyls do. It's a very small sample of that. And then amines. And we talked about the Gabriel synthesis, amine formation, and the amide formation, which I told you the mechanism was almost identical to esterification. So we didn't really talk about the mechanism of that. So let's just jump in and just start hitting some of these problems. Any of the other reactions that you see are probably going to be reactions that we've done already. And so that's why they weren't in the main worksheet. So let's start right here. We've already gone around this wheel partly. We did 3 out of the 4 reactions. Let's do that reaction up top. I have it highlighted. I'm gonna put a date in here so I'll know. But let's do that reaction up top. And let me add a page because I'm gonna show, probably do the mechanism for that too. All right, so look at the starting material, which is that alcohol. And then you're gonna treat that with hydrogen peroxide and sodium hydroxide, followed by a nucleophile, sodium methoxide. All right, let me cut this out. Well, actually, I'll leave it, and then we can do the product first, and then we'll talk about how it happened. What is that first reaction? We learned that in part 1, right? The alcohol is not going to react in this case. In this case, we have an alkene, and we're going to treat it with hydrogen peroxide and sodium hydroxide. What kind of reaction is that from part 1?
Is that where it decomposes, or like dehydration or something like
that? Not quite.
Okay.
But it is a reaction that we learned in part 1 of alkenes. You can do it one or two ways. You can do hydrogen peroxide and sodium hydroxide, or you can use another set of reagents. You can use MCPBA, and it'll give you the same outcome. Anybody remember?
Is this something with adding hydrogen?
Well, actually,
wait, is it the hydro? No, never mind.
No, that is one of the reagents for hydroboration and oxidation, but this is not that. This is actually going to give us an epoxide. So we're going to get this. I'm going to abbreviate the ring. So we'll get that. And then it's the sodium methoxide is just going to open it up, right? That's that nucleophile is going to end up, and I'm going to show you, we're going to do the mechanism for this, and I'll show you how it works. But that final product is just going to look like this. So that, and then OME. All right, so I'm going to take this, I'm going to copy it. And I'll put that on a blank page so we can talk about it in a little bit more detail. All right, so the first step, again, if I take that, if I take the start material that I had, which is this, and then I treat it with hydrogen peroxide, right? That's going to give me this epoxide. Then when I treat that with sodium methoxide, right, that's kind of the reagents. You need sodium methoxide, but you're also going to have to quench it to get to the to protonate the epoxide oxygen. I'll show you what I mean by that. So this is just going to open the epoxide. The methoxide anion is your nucleophile. Sodium is just a counter ion. And the thing about epoxide openings is that the thing about the epoxide opening is it's kind of going to be dependent on the substitution pattern of the epoxide, and it's going to be dependent on the conditions. So if it's under like neutral conditions, it's going to open at the least substituted site. Right, so you can look at the epoxide and see that you got two places where you can open it, right? You can open it here, or you can open it here. Right, so this side right here would be considered the least substituted. Sorry about that. My palm hit the screen. Right. So the methoxide is going to attack here and just pop that open like that. Let me shrink this down to make some room. All right, so I'm going to get an intermediate from that looks like this. Right, where this is O. That's negative, so that's where that sodium is going to end up hanging out. And then on the other carbon, I have the methoxide group that open that up. So that's obviously, you're going to have to quench that, right? So you can just add in any proton source and that'll quench it. So that's an example of an epoxidation followed by an epoxide opening. And the reason I didn't put, again, why that wasn't on that main sheet is because we did this in part one. Epoxidation and epoxide opening. But if you have a epoxide, if it's under neutral conditions, then it's going to open at the least substituted site. If it's under acidic conditions, then it's going to open at the most substituted site. I think we got another example in here that we're going to work through as well. So for that reaction, that's all the reactions for that, right? We had epoxidation, we had chromic acid followed by the Vitic, we had potassium permanganate followed by a transit esterification, and then the first reaction we did was that ether synthesis, and then the top one was the epoxide followed by epoxide opening. All right, any questions about that before we move on to another section of this worksheet? All right, so here's the same example or a similar example, right? Both of these are epoxide openings. Here, your nucleophile, and then just for continuity, I'm gonna add this in. So we can just use water to quench it. All right. So over on this side, your nucleophile is a hydride. Remember, lithium aluminum hydride, LAH, is a source of H-. Right, and over here, your nucleophile is the methoxide anion, so OMe. Right. So what should we get from that? From the LAH product? What should the product be from LAH? Right. This is this is under neutral conditions, so the location of the opening is not going to be any different. Right. You can open at either side because both of these carbons are electrophilic. I don't like that yellow. Sorry about that. So you can open here or you can open here. But which side is going to be favored under neutral conditions?
The least substitute.
Least substituted side. So the side that's highlighted in gray, right? So if we would have just, not that, we just draw an arrow from here to here, we can pop that open and then we can see what the product would be in this case. So let's draw it. 1, 2, 3. This is OH. Sorry about that. That's CH3. So this is the carbon right here that's going to be where the epoxide opened, right? So we're going to put that oxygen here. And I'm going to go ahead and make it an OH because the second step is going to protonate it. Yeah. And then on that same carbon, this carbon right here that I had highlighted in, well, let me put it back in gray. It's just now going to be a CH3. Right here it's a CH2. You can see that it's got 2 hydrogens on it. And then over here, it's still got those 2 hydrogens attached to it. And then the new hydrogen is here that came from that hydride. Am I missing a carbon? 1, 2. I think I'm missing a carbon. I'll fix that. Trying to make sure we got the right number of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. All right. Any questions about that? It's the same again. It's under neutral conditions. So the epoxide is going to be opened at the least substituted site. What would the other product look like? If we kept this same, because we can literally keep this same structure, but swap out the nucleophile. What would the other product look like?
So it'll just have the LME at the end.
Yes, it'll have the methoxy group where that where we put that hydride. So I'll just redraw it. So this will be OH and this will be methoxy. Good. All right. Questions? Any questions about that? So again, with the epoxide opening, it's just where the nucleophile is going to attack. But this all goes back to what I've been preaching for since the class started. Everything is built on the same foundation, which is what we learned in part 1. We learned nucleophiles and electrophiles in part 1. You can never escape that. All right. Let's go to here. Both of these are.
Wait, Dr. Russell,
Yeah, go ahead.
can you go up a little bit for a second? Okay, thank you.
You got it?
Yes.
Okay. All right. Let's go here. It says predict the product and propose a mechanism. All right. When it asks you to predict the product, all that means is what product are you going to get from this reaction? Then when it's ask you to propose a mechanism, then you got to show how you got it. So right here, let's predict the products first. Somebody tell me what reaction this is.
Is that the reaction of the carbonyl?
Yes. It will happen on the carbonyl. Which specific reaction is going to happen?
Acetal.
Good. Who is that? I can't see because I'm
Kayla.
on my iPad. Good. So it's acetal formation. Come on, Palm. Right. So when we predict the product, now we know what we're getting ready to do. Sorry about that. Come on, man. Tighten up, Russell. Right. It's acetal formation. So what is the product? Notice the stoichiometry, right? I got 2 moles of my alcohol and I'm reacting that with 1 mole of my ketone. Right. So that's
sorry.
Go ahead.
I was gonna say, like, wouldn't the carbonyl break into 2 ethanols?
Or in this case, we're gonna add, you're right, but if we're adding 2 methoxy groups to it.
Yeah, sorry.
Yeah. I know what you meant though. I know what you meant. All right, so that's that. Come on, man. Sorry about that. All right, so we have that. This CH3 isn't going anywhere. None of the other stuff is going anywhere. The only thing that reacted was the carbonyl. All right, so we have an OCH3 here and 1 here. All right, so that's my acetal. All right, now it asked for a mechanism. So now we got to talk about how we got to it. So let's do that. So what's the first step in the mechanism of this reaction? And I'm going to react it with,
Can I draw on the screen?
yeah, you like drawing on the screen. Come on.
Yeah.
You can just put the arrows in.
I don't see it where I usually see it to draw on the screen.
And maybe because I'm on my iPad. That might
Yeah.
be.
I don't see it.
You can tell me. So that's okay. That's okay. You can tell me where you want to put the arrows, and I'll put them in.
So the first arrow would be going from the double bond to the oxygen, right?
Okay, go to here.
Yeah. And then the nucleophile basically gonna attack and like the middle part.
So we're gonna attack this carbon, right?
Mhm.
Good.
Yep.
So that's the first step is nuclear. Anytime you got a carbonyl and you got a nucleophile in solution with it, you have a nucleophile in solution with it, that's the first thing that's gonna happen. The carbonyl carbon, gotta remember again from part 1, when we first talked about polar covalent bonds and all this stuff, there's a giant dipole here, right? So that carbonyl carbon is partially positive. The oxygen is partially negative, and it's got 2 lone pairs, only 2 that I didn't write in. But so that's the first thing that's going to happen. Carbonyls are great electrophiles, right? So I'm going to end up with this intermediate. Right? The CH3 is still here. And then OH, CH3. Right? Now, how do I get from there to the hemiacetal? Where the O minus becomes an OH.
Wouldn't the arrow go from the oxygen to the hydrogen?
Yes, good. We're going to do a proton transfer. Inter or intramolecular? Which one? What is it when everything is happening within the same molecule? Is that intermolecular or intramolecular? Wouldn't it be intra?
Yes, it will be.
Mm-hmm. So it's intramolecular proton transfer. You pull off the proton from that OH, and then the electrons in the OH bond go back to oxygen. So that's how I get to the acetal. So I'm here. Now I have another. Let me draw that the opposite way. And now I got another alcohol, right? But there's no, this time there's no, the carbonyl carbon is not electrophilic because it's got a full octet and all that good stuff. And it's got, it's got some dipoles to the oxygens or whatever, but it can't accept a nucleophile outright, even though we can eventually replace the OH group, and we will. It's not direct, right? So now I need to do what? I want to turn that OH into a better leaving group so I can get rid of it. What can I do?
You got a protonated.
Good. Yeah, you're right. Be confident. We're going to pick up a proton from here. Right, and that's going to give me, I'm going to cheat this time. Don't tell nobody. It's gonna be that. Copy. And now I'm gonna have, I'll write out both protons so it doesn't look so goofy. Right now we got water as our leaving group. And this is gonna be plus OCH3 minus, right? And then when we did this the other day, which way did y'all prefer? Did y'all prefer like the carbocation formation, like the spontaneous route, or the neighboring group participation route? I can't remember.
I like the
remember,
spontaneous route.
remember we said that this could go either way, right? The methoxy group there or here could force that out with a lone pair, or it can leave spontaneously. So we'll just do that. So let's say that leaves. And then I am sorry. I'm here. And I'm gonna draw that with the right geometry too, since I messed it up. And now that's positive. And then my methoxy anion is still here. So now that's how I'm able to get to the acetal, right? Because all it is now is what happens here. Ooh, that's a bad spot for those electrons, right over that I. What's my final step?
The that attacks the positive.
Yeah, it's just a nucleophilic attack on the plus charge. Let me do something right quick. So it's just an attack here. And that's how I get to my acetal. I'm just gonna write it in. Right? So when it asks predict the product, that means just draw the product, whatever. That's why I'm telling you, flashcards, reps, because you got to be able to recognize the reagents in order to be able to know what product you're going to get, what type of reaction it is. So predict the product means exactly what it says, draw the product of whatever the reaction is. And then propose a mechanism means how did you get there? What are the arrows and the reactions that are happening to get you from point A to point B? All right, questions about that? That reaction. All right, let's go to the second one. Same thing, predict the products first, and then propose a mechanism. So what's the product from this? What type of reaction is this, first of all?
Wait.
Okay, it's a Wittig reaction, which does what? So the Wittig is a way to do what?
Turn aldehydes into carbonyls. Well, carbonyls. Well, right? Or ketone.
No. So let's say so aldehydes and ketones are carbonyls, but the Wittig converts them into alkenes.
Oh yeah.
Right?
Sorry.
That's all right. I could tell it's early. I can hear it. It's Monday too. So yeah. So the Wittig is a way to convert aldehydes or ketones into alkenes. What's the shortcut way that we learn? So this is where it helps when we talk about predicting the products. You don't have to go through the mechanism if you know what the outcome of the reaction is. So I taught you a kind of a shortcut method to predict the product, if you were paying attention.
You said that we had to we could do like, well, I know like in last class we did we subtracted like HX from the alkyl given.
From the alkyl halide. And it's got to be from here. It's got to be from the carbon where the halogen is. You can't take it from here. You're gonna have the wrong product. All right. So I'm gonna, and again, this is not a necessarily a scientific, Nobel Prize winning method, but it'll get you to where you need to be. If you subtract out HBr, what I'm left with is CH3, CH. And this is the carbon right here that's going to replace oxygen and convert that ketone that we have into an alkene. Right, so the product is going to look like this. H and then CH3. And the reason again why it has to be this carbon where you take the hydrogen from is because in the mechanism you can see right away that that's the carbon. And let me fix that because that is a typo. You can see right away in the illid that that's the carbon where your negative charge is going to be. I thought I fixed that in this handout. Maybe it was in another handout. Thank God for technology. All right. So the illid is we already made it. Right. That's just reacting the alkyl halide with the triphenylphosphine and then using KOH to pull off one of those protons. So for the mechanism, we can start at the illid plus the ketone. What's the first step? I have an illid.
The illid's gonna attack.
And it's got a pair of electrons. So it's, come on, Russell. It's gonna attack right here, right? Remember that carbonyl is a great electrophile. So if you got a nucleophile in the same pot with it, they're gonna have a little interaction. All right, so from that, I'm gonna get this intermediate, which we talked about. I'll write it this way.
I have a question.
Go ahead.
So is it gonna form the same intermediate every time?
Yes.
Same type of intermediate?
Same type.
Okay.
So then you'll have this. And I'll explain it because I'm gonna leave it in skeletal form. Right, so this is my illid carbon right here, the CH, and it's connected to a CH3, which is right here. And it's also connected to phosphorus, which is right here. So it's the same 3 atoms right there. All right. So that intermediate is gonna cyclize. Is that right? And this is positive, by the way. Right, that doesn't stay like that. It actually cyclizes and then decomposes. So how do I cyclize it? I have an oxygen with a negative charge next door to a phosphorus that's got some.
So that oxygen's gonna attack.
Like this, right? And then that's gonna give me a 4-member intermediate, like that looks like that. Right, and once we get here, forming the product is just a formality. right? It's just a formality because this thing is going to break down and give me the product, right? I want an alkene as my product, so I want to put a double bond here, right? And then the other product that I get, the phosphine oxide, is going to have a double bond here. And I don't have a lot of electrons to use, but I actually can use the 2 sigma bonds. We talked about this the other day. I'm just kind of reiterating it. We can use the 2 sigma bonds here and here, and that's how that breaks down. So I end up with this alkene, and then on the other side is here. And then plus that, right? Questions? Any questions about any of that? Right, we didn't really go through the illet formation. I kind of gave that part to you by giving you the illet, but the illet formation is normally you take the alkyl halide, you do a substitution with triphenylphosphine. Your halogen is your leaving group, so it's like an SN2, and then you just do proton transfer with that base. That's the purpose of that KOH. All right. Any questions about that? You need to see that part because I can put that in too. All right. We'll come back to this. I'll let y'all do this because we've already done aromatics. So you can do that on your own. We'll come back to that too. Let's do this reaction wheel, right? Let's see if we can finish. So we'll start at the top. I have potassium permanganate, which is an oxidant, and then I have methanol. So what is the result of the first reaction?
You'll get a carboxylic
Anybody?
acid.
Who that? Who is
You'll
that?
get a carboxylic acid, Kayla.
Okay. Yeah, you're right. You're right. You're right. You're right. I just want to make sure I give credit to who gave the answer. So you're right. The first, and I'm gonna write this out just because I want us to be able to keep track of everything. So you're gonna get that because potassium is a superoxidant, and it'll take primary alcohols all the way to the carboxylic acid. And then what about the second reaction? Because we have methanol, now you got an alcohol with a carboxylic acid. What do you get from that?
An ester.
Right, that's an esterification. Where again, even if you don't know how it works, you can look at the alcohol, pick out the alcohol of it here, and swap that H group with it.
Okay,
Right,
I
so
have a really quick question.
Product from that. Yeah. Go ahead, you can ask it.
Okay, so can you tell me the main difference between the trans esterification and the regular esterification? I know one requires a catalyst and one doesn't, but I guess I'm just trying to figure
Oh, you mean
out why
what we
that.
did with the acid chloride?
Uh-huh.
So with the trans esterification, you're basically swapping out the OH group with the alkoxy group that comes from an alcohol. with the esterification using the acid chloride, you don't start with a carboxylic acid. You actually start, this is actually will be a chlorine. Now the alkoxy part is still gonna come from an alcohol, but your starting carbonyl is gonna be an acid chloride instead of a carboxylic acid.
Yes, sir. Thank you.
All right. Oh, shucks. I'm trying to do that. Hold up. All right. So then the final product is going to look like this, not like that. And that's going to be plus water. All right. Let's do the second reaction down here at 3 o'clock on the wheel. What do you think? Got strong base, followed by alkyl halide in the presence of alcohol.
Williamson.
Okay, good. Williamson ether synthesis, good. This is O, and that's ethyl, CH2, CH3, right? All right, good. Let's do the reaction at 6, right here. What type of reaction is that? Very first reaction. It's important with these sequences that you understand once I do that first reaction, right? I'm no longer going to be acting on the starting material. I'm acting on the product from the first reaction. So that first reaction, what type of reaction is that going to be? You got chromic acid, you got a primary alcohol.
You'll get aldehyde.
Yes, that you're going to convert the alcohol into an aldehyde. Good. So that's the oxidation part. And then the second reaction is going to be on that aldehyde. So what am I going to get from that? I have it written right here. That is acidic. So what's the final product going to look like?
Would it just be a CH attached to it?
Yes. If you subtract
that.
out HX, yes. What you're going to be left with is CH2. So yes. Sorry about that. All right, so that's the final product. If you look at the Vidic reagents, you have an alkyl halide, which is eventually where your carbon is going to come from for your alkene, and triphenylphosphine, KOH. Anytime you see this with an alkyl halide, it's going to, you can bet that it's going to be a Vidic reaction. All right, let's do the next one. We've seen this chromic acid with this alcohol already, so we know we're going to get an aldehyde from that. Right, that's the product of the first reaction. What about the product of the second reaction? What is that going to be? All right, so the oxidation part is done. And now we're going to make an imine. What is that going to look like?
Will the NH2CH3 replace the O?
Yes, Yes, you will. That will replace the oxygen with nitrogen, but you're also going to lose water, and both protons are going to come from here, right? So it's going to be in CH3 like that, and then everything else stays the same. I'll just abbreviate it. So that plus water, right? Because you know your nitrogen, it can only have 3 bonds to it. So otherwise,
Okay, so that's why we have to take off one of them. Okay, thank you.
So you end up losing both protons, and that's how you get water to leave as a leaving group, because both of those protons end up on oxygen. All right. We got 8 minutes left. I'm gonna leave this one because all you're doing here is putting the arrows in. So I'll leave that one. And let's see. I'll leave this one too. All right, what about here at the top? It says predict the product and propose a mechanism. What type of reaction is that going to be? You have an epoxide in the presence of a really good nucleophile, hydride, a good hydride nucleophile.
Wouldn't that be a reduction?
It is a type of reduction. Yep. But in this case, where are we gonna add the hydride? So in this case, the epoxide is symmetrical, right? So it doesn't matter which side we open it from. So let's just pick a side. For as far as the mechanism is concerned, this is negative. It's coming here. You're gonna pop that open. So you end up with this. Hydride it was added there, and then this is O minus, and then followed by H plus. That's what the water is for, just to quench it. Right, so that would be the final product from that. You opened it with LAH, and then you quenched it with water to get that alcohol. Right, questions? Any questions so far? We got 5 minutes. Let's do, go ahead.
Can you go up a little bit? All right, thanks.
All right. Let's do a couple of these there. Do this reaction right here and this one. All right. What's the product if I take that aldehyde in the middle of that wheel and treat it with that Grignard followed by water? What would I get? Remember that aldehyde is an electrophile, very good electrophile. And then the Grignard is a nucleophile. And this is the nucleophilic part of it right here. So what am I going to get from that? This doesn't change. Wouldn't I get an alcohol?
Yes, I wanted to say that, but I wasn't sure.
Remember the mnemonic? Granular plus aldehyde or ketone equals an alcohol. It's an old reaction. We've done it before, but I just stuck it in there because, yeah, it's one that we should remember. All right. What about here? The other second reaction that's highlighted. All right, none of this changes. We just did this reaction, just with a different
Yeah, you'll
alcohol.
get two things of CH3, CH2O.
Like that. Is that right?
Yes.
Right. That's a acetal reaction. 2 moles of alcohol, 1 mole of aldehyde or ketone. You're gonna get an acetal. All right. We're gonna stop here. We'll pick up on Wednesday. And
So
yes,
are we gonna have a review session before the exam, like on that
before the
Thursday?
final or before this test?
I mean, for both, honestly.
Yeah, we'll definitely do a review for the final because there's a big gap between the last, well, not a big gap, but there's a gap between the last day of class and the final. So we can pick a day and do a review. For this test, since we're done with the most of this handout, like Friday during class, that'll be we can actually do that time as a review.
All right.
That's rather than starting a new section, because this is the last week of class. That's crazy.
Dr. Russell,
Yes.
so the exam will be taken that Friday, not during class?
Yeah, but it's gonna be on responders though.